Hello! This video will explain the concept of pulse width modulation, or PWM, when applied to LED brightness control using Python with Raspberry Pi. Using PWM is a common method to control brightness of LEDs, whether they are small, what we use on a breadboard, or in standard household lighting. Pulse width modulation relies on rapidly cycled DC power, resulting in a square wave. The brightness of the LED is proportional to the size of the pulses, otherwise known as the duty cycle. The wider the PWM pulse, the brighter the LED. Let me demonstrate how it works with the Raspberry Pi. GPIO 0 library has the PWM LED class suitable for that application. This class has a pulse method which will smoothly vary the LED brightness. It also has a value property which takes a floating point number between 0 and 1, allowing to set the LED brightness from off to fully on respectively. I have 3 LEDs on my breadboard, and each of them uses the pulse function in a different way. The left side LED uses pulse with the default timings, 1 second to ramp up and 1 second to wind down. The middle LED starts with full brightness and then slowly fades away over a period of 2 seconds, while the right side LED comes on to full brightness over 2 seconds and then dims over 2 seconds. Have a look at this in action. Although this is software-based PWM, which makes it subject to some amount of jitter, this actually works quite well. Any flickering that you may see right now is just video recording artifacts, as the LEDs pulse at 100 Hz, while I record this at 24 frames per second, so this does not align perfectly. In real life, that actually looks pretty good. The pulse method is useful if you want to have this effect. You can control the timings, and it runs in the background as a separate thread. There is no need to have your own loops, and the brightness levels change very smoothly. Setting the PWM LED value property is another way to control the LED brightness. The value property number refers to the PWM duty cycle. My example sets the duty cycle at 3 different levels, from 100 on the left to 25% on the right. If you really look at them, the brightness is not that different. That's because LED brightness follows a logarithmic curve when using PWM power. This makes the value property difficult to use, as it is hard to predict what the relative brightness will be for a given duty cycle. This is particularly problematic when attempting to have gradual changes the way the pulse method works. Let me illustrate that using a spreadsheet. The logarithmic LED characteristic results in brightness levels changing rapidly on the low end of the duty cycle and behave the opposite way on the upper end of the duty cycle. This spreadsheet models what is happening right now on my breadboard. Keep in mind that this chart and calculations formulas I used are just an illustration. I do not have the spec sheets for my LED, and I didn't perform proper analysis here in terms of measuring the light output levels for given PWM duty cycles. We need to compensate the LED characteristic with PWM cycles that work in the opposite direction, following an exponential formula. Perhaps the simplest formula would be the power of 2. The orange curve on the chart represents the compensated PWM cycles, calculated using the powers of 2 formula. The resulting LED brightness curve will be an average between the LED characteristic and those compensating values. Ideally, the brightness changes should follow a straight line, but in practice, that is not achievable, as each LED is different. We are trying to get something that is just good enough, not perfect. Let's use this formula in Python code to see how the LEDs will behave. I will use a loop for the 10 brightness levels so you can see the changes in sequence. In this example, I use 2 LEDs. The one on the left side will change brightness in equal 10% duty cycle increments, while the middle LED will have its duty cycle changed according to the formula. You may have noticed that the LED on the left increased in brightness quickly, and at around 60 or 70% duty cycle, the changes of brightness were pretty much unnoticeable. The other LED behaved much better, with the changes in brightness appearing more constant. Let me run this again. Observe what's happening early, below the 50% brightness for both LEDs. This compensation method is alright if you have a relatively small number of steps. I played around with the numbers, and for this model, you cannot really get much past 10 steps. Let me show it to you on another chart. This is the same situation as before, and the only difference is the number of steps increased from 10 to 50 with the same formulas. Notice how the chart has changed. My concern is here at the low end of the PWM duty cycle, where nothing is really happening until the mid-40s. You could fiddle with the formula. For example, if you add a square root to it, you will notice that the situation improves, but the changes are just not good enough. If you want more adjustment steps, you need a formula that is more sophisticated. A number of ready formulas are used, and here's one that I tried and it works for me. This formula uses logarithmic calculations to provide very favorable brightness adjustment, and it works well for up to 100 steps. You can see in this chart that the brightness line is almost straight, which is very good. Again, this is just a model, and in reality, the result may not be as good or will be different, and it will vary between different LEDs. Let's see how this formula works with 10 steps for my LEDs. Here's the updated code. There's a new input from the math library, initial calculations to get the fade factor that affects the shape of the PWM curve. The code for the two LEDs used previously is unchanged. The left side LED is uncompensated, and the middle LED uses the power of 2 formula. Now I also have a third LED which will use the latest formula. The program will display all 3 PWM duty cycles as it goes through the 10 steps. Let's run it. That looks much better. Let me do this again. Pay close attention to how the middle and right LED differs. Notice that the last formula provides the best results across the entire range of 10 steps. The advanced formula adjusts very well for a larger number of steps, which is important as you may want to go up to 50, if not 100 steps. 100 would be ideal because then you can relate the steps directly to brightness percentage. This spreadsheet illustrates the situation with 50 steps. While the resulting brightness curve approximation is far from being straight, I think it's very good. I yet have to see any household LED dimmer that does better than this. Typically, they don't fade very well on the lower end, so this is perfectly acceptable considering what the industry does today. The only complaint I have is that this formula is not very pretty. It makes sense to, at the very least, to put it in a function. This way you clean up your program and avoid duplicate code if you use it in more than one place. Here's what the program would look like after this. Of course, this doesn't change the way the program works. While I used loops to demonstrate this concept, this formula can be used directly with the value property of the PWM LED, similarly to what I did at the beginning of this video, but now the values will not be referring to PWM duty cycles, but to brightness levels, making it a lot easier to understand and work with. Here's the idea. With the number of steps set to 100, the numbers used with value are essentially brightness in percent. I think this is way better than what it was initially. You can actually tell the difference in brightness from the left 75% versus 50 in the middle and 25 on the right. This approach will work in many applications, but be cautious when using it with loops, as there is a performance hit every time the calculation is done. If you were to make that calculation many times per second for multiple LEDs at once, it may be better to pre-calculate the values and use them as a lookup table. Since I have these numbers already in my spreadsheet, placing them in a program is actually very simple. All I need to do is to copy the values from the spreadsheet column into my program and put it in a list. Let me show you how that would work. Here is the finished product. Notice I got rid of all the calculations and I have instead a large list of 50 pre-calculated entries. Of course, you could have 100 values or any other number of steps you like. Since I have 50 values, numbers 40, 25, and 15, used with the value property referred to 80, 50, and 30% brightness respectively. A lookup table such as this one will work the same as the calculations, but it will be more efficient in terms of program execution speed. Notice that to look up the values now, because it's a list, we use square brackets and not parentheses like before. Let's run it. Again, any flickering that you see has nothing to do with the code. It is just a shortcoming of the video recording. Since the lookup table is a list, it is very easy to use it with loops to implement functionality similar to the pulse method. Ideally, such code should be run as a thread, but I discussed threading in a separate video. Of course, you can loop through the list in reverse order too. I have included links in the video description to the lookup table values for 50 and 100 steps. Feel free to use them in your programs. I hope you enjoyed this video and learned something. Thanks for watching.